Hello and welcome to the second video of section 2.6 on implicit differentiation. In this video, we extend our differentiation techniques on explicitly defined functions to implicit functions. Let's revisit the final example from the first video of this section. The equation x cubed minus 6xy plus y cubed equals 0 defines the curve. The curve is not a function, but it implies the highlighted function. In the highlighted region, y depends on x, so we denote it y of x, just as we've always denoted functions such as f of x or g of x. As the left and right hand expressions are equal to each other, the derivative of both should be equal. As we take the derivative, we need to remember that y of x is a function, so its derivative is y prime of x. As we take our derivative, be sure to use the product rule on x times y of x, and to use the chain rule on y of x cubed. We've taken the derivative of the equation, and now we have a mess. What were we looking for when we derived the equation? The equation implicitly describes the function where y depends upon x. So by deriving with respect to x, we were searching for the derivative of y with respect to x. In other words, we were searching for y prime. But before we go on to that, now is a good time to drop the prime notation in favor of the alternative Leibniz notation. The Leibniz notation is more descriptive than the prime notation, in that dy over dx denotes the derivative of the variable y with respect to the x variable. The prime notation will be problematic when we run into multiple variables. Suppose y depends upon x, but what if it also depended upon another variable, t? Y prime could mean either dy dx or dy dt. Besides being more descriptive, the Leibniz notation clearly stands out in an equation. Rewriting the derivative of the equation in Leibniz notation, and rewriting the function y of x as just y, we see that the derivative dy over dx is implicitly described by both x and y in this equation. We are interested in the derivative dy dx. In this equation, dy dx is implied by x and y, but we can solve for dy dx and write it as an explicit function. Begin by distributing -6. Then, isolate on the left the terms that have dy dx in them. Factor dy dx. And then divide the factors which do not have dy dx in them to the right side. And we obtain an explicit function describing dy dx. For example, when we take a point on our function, say x equals 3 and y equals 3, notice that our choice of x and y plugged into our original equation makes that equation true. Therefore, x equals 3, y equals 3 is a point on our curve. We can calculate dy over dx at the point 3, 3 by plugging x equals 3, y equals 3 into our equation, which implicitly describes the derivative. Take a second to solve for dy dx. Your answer is -1. Let's clear up the calculations we just performed. When we take the derivative d over dx, we are measuring how a function's output changes with respect to x. The derivative of x with respect to x is 1 because x changes at the same rate as x. As we saw in our earlier calculation, if y is related to x, we write y of x for the function. Then the derivative of yx is dy over dx, which we shorten to d dx of y is dy over dx. We also calculate the derivative of the function y of x cubed, and we used our chain rule to obtain 3yx squared dy dx, which if we rewrite y of x as y, to find that the derivative with respect to x of y cubed is 3y squared dy dx. To summarize, when taking the derivative of an expression, proceed with our differentiation rules as normal. In this case, we use the chain rule, differentiating the outside, leaving the inside alone, and multiplying by the derivative of the inside. And continue to differentiate as normal until forced to differentiate y, which we'll denote as dy over dx. In fact, whenever you take the derivative of a variable, unless you understand the relationship between the variable and x, you denote this relationship as dt over dx if the variable is t, or dr over dx if it is r. Further, it doesn't need to be x that you are differentiating with, it could easily be y or t. When a function is defined implicitly through an equation, there is no need to write the function explicitly in order to find the derivative. Just take the derivative of the left and the right hand side individually. We calculated the derivative of the left-hand side earlier, and the right-hand side is just 1 plus dy dx. The derivative dy dx is expressed implicitly here, however you can find it explicitly. factor dy dx, and divide, and we find an explicit description of our derivative. Note, however, that you need both points x and y to determine the derivative. The derivative obtained through implicit differentiation is still a function representing the slope of the tangent line for a point on the graph. Taking the derivative with respect to x, differentiate as normal. The derivative of x squared is 2x. The derivative of y squared is 2y dy dx. We need dy dx because y is not x. And the derivative of the constant 9 is 0. Find dy dx explicitly. When x equals 0, the tangent line has a 0 slope, meaning it is a horizontal line. We can see that at the top and the bottom of our circle. When y equals 0, the tangent line has an undefined slope. Here it is vertical. You can see that on the left and on the right of the circle. Not all functions depend on two variables. The function x squared plus y squared plus z squared equals 0 describes a relationship between x, y, and z implicitly. Taking the derivative with respect to x, we can still find the derivative dy dx, the change of y with respect to x, though we will also have the derivative dz dx when we take the derivative with respect to x, as z is also related to x. We can solve for dy dx implicitly by isolating on the left the terms that have dy dx and then dividing away the term that does not have dy dx. In the same way, we can explicitly write dz dx by first isolating on the left the term that has dz dx, and then dividing away the term that doesn't have dz dx. So the relationship dy dx depends upon more than just x and y. It also depends upon z and dz dx. In the same way, dz dx depends upon x, y, z, and dy dx. To summarize, implicit differentiation differs from our previous techniques in that when you encounter a variable different from the one you are differentiating with respect to, you pick up an extra term. In most cases, you will see dy over dx, but as we finish Chapter 2, we will encounter other variables. Something to consider before class: how would you calculate the second derivative of an implicit function?